Now again, what we're doing today is very, very similar to what we've been doing in the past, except I'm actually going to show you how I came up with all the equations that we worked with. And we only worked with 3. There's many more, or many more ways that we could arrange these types of variables around. One thing that I want you to realize or look at is that when we look at the 3 equations that we use, now notice that Dalton's law for partial pressures isn't in here. But when we look at Charles, Boyle, and Avogadro, which variable shows up in each one of these? The volume. So what we have in Charles is a temperature-volume relationship, and Boyle it's a pressure-volume relationship, and in Avogadro it's a number of moles volume relationship. There's many more other combinations that we can look at, but what we can do is we can take all of those variables and combine them into one simple equation, which is called PV equals nRT. Now, the one variable that doesn't or shouldn't be recognizable at this point is the letter R. And that's taking all of these variables under a set of standard conditions and determining this gas constant. So the universal gas constant is called R. And it's got a really crazy unit on it, which I'll show you once we start doing some of the problems out on the board. But this is the equation that we'll be using for the rest of the year when it comes to gases. And when we get back from spring break, we'll be doing some stoichiometry with this equation and a lot of other fun things. However, all of the problems or all the equations that we came up with come from this, and I'll show you how we did that. Okay. So the ideal gas or the universal gas constant can be found by using a set of conditions. Now, I do want you to make a change on your notes. I have a capital R here. That should be an N, a lowercase n. I don't know why it says R. So if we take the equation PV equals nRT and we change that to find out what our standard conditions are, there's a term that we'll use when we get back from break called STP, conditions at STP, which are conditions at standard temperature and pressure. At the standard pressure, it's 1 atmosphere. It's about what we're experiencing today on a nice sunny day outside. The temperature is at 273 Kelvin. How many degrees Celsius is that? 0. Not very ideal if we're going to be working with gases. And it represents for 1 mole of a gas. Now, if we have 1 mole of a gas at this pressure and this temperature, this is the volume that it will generate. When we get back from break, that 22.4 liters is going to be pretty important. I mean, it's a number that we'll use, and it will save you a lot of time if you can memorize 22.4. So getting all of these variables plugged into the equation where we have PV over NT gives us this constant. Now look at that unit. It's atmosphere liters per mole Kelvin. That's a big one. Okay, so that actually has 4 units within it, and we're always going to be showing that. And if you allow the units or plug the units in, they'll tell you if you're doing the equation correctly or not, which is kind of cool. Now, since we can work with atmospheres, we can also work with kilopascals. So everything's the same except for the kilopascals. In that case, 1 atmosphere is equal to 101.325 kilopascals. So the 2 R's that we could be using, or the ideal gas constants, depending on if we're in atmospheres or kilopascals, and these will be given to you. So it's not like you have to memorize them. It's just a matter of being able to use them. Here's an example problem that I worked out in the notes. Don't worry about that. Let's do this first practice problem. Page 3. Let's grab one of those. Again, we'll be using this equation, PV equals nRT. This is our R value per mole Kelvin. Okay, so that's what R is equal to. That's a constant.
What's R stand for?
It's an ideal gas law constant, so that'll be given to you. So that is what the R represents. Again, the P is pressure, V is volume, N number of moles, and T temperature.
Is this going to be on the quiz?
Could be, if you wish to use it that way. That's what I'm saying. What I'm about to show you is another way of working out the problems that we worked out before today.
But we can use the other method.
Depends.
Basically, this isn't really new.
It's not new, it's just another way of how I got all that stuff. Yeah.
And every formula will be given.
What, should we just like?
We'll see.
Not
See.
that.
All right, number 1 says calculate the pressure of a 159.53 gram sample of chlorine gas at 53.5 degrees Celsius and occupying a volume of 150 centimeters cubed. So, of these variables, which one are we looking for? P. So since we're looking for P, that means we want to get all the unknowns on one side. So I'm going to divide V on both sides. So now my equation looks like this. Okay. So we have our pressure is equal to the number of moles times the ideal gas constant times temperature divided by volume. Now, before we can plug any values in, we have to make sure that the units for all these things are in atmospheres, liters, moles, and Kelvin. We have to convert. We can't just throw in the values that we have. So the first thing right off the bat there, we have 159.53 grams of what? Chlorine, or Cl2, right? So we need to change that into moles, because again, we're looking for moles for our N here, and that's Cl2, so 2 times 35.45, which equals something. So is it 2.25 moles? Okay, so we have our first thing, 2.25 moles of our gas. The R is a constant, so what we'll do is we'll write the 0.0821 atmosphere liter. Now again, I'm not a big fan of multiple division lines. Since the mole Kelvin is on the opposite side of the dividing line as atmosphere liters, let's put it on the opposite side. Okay, because having multiple division lines can get a little muddy there. And besides, we want it down here. We want to be able to cancel alike terms out anyway. So there's our R. The temperature is 53.5 degrees Celsius. So what do we do to that? At 273. So what is that? 0.5, 6, 13. Oh, sorry, 12. No.
326.
What is it? 326. There we go. So 326.5 Kelvin. And then the volume is 150 centimeters cubed. Well, that's cool. If I'm looking at centimeters cubed, how do I get that to liters? In other words, what's a centimeter cubed equal to in metric? 1 milliliter. So knowing that 1 centimeter cubed is equal to 1 milliliter, that kind of makes things nice. So 1 centimeter cubed equals 1 milliliter. And I need to get this to liters, so 1,000. Good. So there's 1,000 milliliters. So really that's 0.150 liters. So we'll put that down here. So when we look at this, what units can cancel out? Well, moles are gone. Good. Kelvins are gone, and liters are gone. They're all gone except for atmosphere, which is our pressure unit. So whatever that all equals out to be. So like 402, and that's ATMs. So that's a lot of pressure. All right, so the minimum, well actually you'll need to show me all these conversions. So again, show the equation rearranged before you start throwing anything in. Okay. Now that's not bad because that's a set of conditions. I don't think we had any sets. Number 2 it says, calculate the number of moles of nitrogen gas if the volume is 30 liters at 107 kilopascals and a temperature of 298. Now the other R value is 8.31, and that's kilopascals liter per mole Kelvin. Okay, so I will give those to you. The only thing that you're going to have to recognize is if you have atmospheres as your pressure unit, this is the R you'll use. If you're given kilopascals, that's the R that you must use. Okay. All right, so we're looking for the number of moles. which is N. So what do we need to do to R and T? Divide it on both sides. So now the equation looks like this. We have PV over RT is equal to N. And I need to see that before we start throwing any values in. The pressure is 107 kilopascals. Do we need to do anything to that? No. It's already good to go. The volume is 30 liters. Is that one okay? Yeah. Again, we want to make sure that we have the same units that's in our R, so we can cancel them out. The R value, which R should we use? The first one or the second one? The 8.31. So we'll plug in 8.31, and that's kilopascal liter. And again, I'm going to put the mole Kelvin on the opposite side of the dividing line, so that goes right there. So instead of drawing a division line and putting mole Kelvin here, just put it on the opposite side. Cleans it up. Temperature, wow, 298 Kelvin, so we don't have to do any conversions there. Okay. And so canceling out of like terms, kilopascals are gone, the liters are gone, Kelvin's gone. What unit remains? Mole. Which is N. So find that out. And probably the hardest part of this problem is making sure that you actually use the correct R value there.
And how do you know which R value to use?
Look at your units for pressure, kilopascal, kilopascal. If it's atmospheres, you need to use that one.
Okay.
Yeah, always be aware of your units. So what is that, 1.30? And that's moles. Now, if I were more adventurous, I might even ask you to convert that to grams. So if I told you if we had that many moles of nitrogen gas, okay, then we could easily convert that to grams. So be sure you can still do that. So the ones are part of your homework? Looking at the next part. Okay. Now, this is explaining what we did before today. Okay. We had a before set of conditions and an after set of conditions. And we never talked about the other set of conditions. I may have said in some of the problems that the pressure and the volume don't change type deal. Well, if you don't see values next to those, that means they remain the same. So when we look at it, we're actually going to be using PV equals nRT twice, and we'll identify which variables we're going to be using from that. Pretty straightforward. It'll make a lot more sense once we work one out on the board. So let's take a look at the next example. So we've got two practice problems there. Practice problem number 1, or the first one there, says a sample of hydrogen gas at a temperature of 40 Kelvin changes to a volume of 40 liters at 30 liters. Question is, what is the new temperature after the reduction of the volume? Bless you.
Thank you.
So we will be using PV equals nRT twice. Okay. So you have a initial set and then a final set. Now also what you may want to do, not necessarily at the beginning here, but once we get into the little more fun problems, is identify the variables in which we're using. So we have an initial pressure, an initial volume, initial set of moles, an initial temperature, and then we have a final pressure, a final volume, a final number of moles, and a final temperature. Okay. So we actually have 8 variables that we could be working with. Okay. We could be working with them. So when we read the question again, it says a sample of hydrogen gas has a temperature, T1, that changes its volume, P1, to 30 liters, V2, and the question wants to know what is my final temperature, T2. All right. So having that information, we can go ahead and write down what we know. So we know our P1, or our initial, I'm sorry, not pressure, these are volumes. There. So our initial pressure, what does it say about the pressure in this problem? Do we know anything about the pressure? No. So since it's not said, or I don't say anything, assume it to remain the same. So P1 is equal to P2. and that's a good assumption. Okay. The volume initially was 50 liters. Let me write that down. And it went to 30 liters, so it decreased. The temperature was at 40 degrees Kelvin. So how many moles did we have initially? We don't know. So if it doesn't mention it, assume it to be the same. So N1 is equal to N2. So we can also do that down there. And T2 is actually what the question's asking for. So question mark. Okay. So there's what I know. So what I want to do is I want to make sure that I have all my known variables on one side of the equation and all my unknowns on the other. So put the knowns on one side, the unknowns on the other side. So I know V1, T1. But look, since I'm looking for T2, should I divide T1 or should I divide V1 on both sides?
Wait, what was the question?
Okay, again, I'm looking for T2, so should I divide T1 on both sides or should I divide V1 on both sides? And I'm looking at this top one first.
V1.
I'm going to divide V1? Okay. So I want to make sure that I have T on top since I'm looking for T2. So I'm going to divide V2 on both sides. So now my equation looks like this. Okay. So I have all the knowns on the right side. Okay. You could put them on the other side, but just make sure the variable you're looking for is on top. Then what I need to do is I need to get all the unknowns to the other side. So I'm going to divide N and R on both sides. So now my equation looks like this. Actually, let's write it up here so everybody can see it. P over NR is equal to T1 over V1. Okay. So now I have. So now what I have is all the knowns on one side, all the unknowns on the other side. What's nice is I'm going to do the same thing with the 2's, but I'm not going to do the same thing actually by writing it down. So that's telling me that this equation exists. Okay. So we don't know what these are, the pressure, the number of moles. We know what R is, but we really don't care. So now we have this equation, which should look familiar. Okay. So that's what we did beforehand. So that's how we actually got these, by using a before and after set of conditions for PV equals nRT. So then we're looking for T2, so that means we're going to multiply V2 on both sides. So now my equation looks like this. T2 is equal to T1 times V2 over V1, and we'll solve it. Okay.
I feel like it would have been a lot easier to skip the whole first part.
Yeah,
To that equation.
I agree.
I agree, but we're not always going to have the three scenarios. We won't always be Boyle, Charles, or Avogadro. So we could have a pressure-temperature relationship. We could have a volume and a number of moles relationship, or we could have different scenarios. You're going to have more than just two variables to work with.
Right, watch out. I need to take a picture of that so I don't forget it.
It'll be online. And then what we're going to do is, once we have this, now we just plug in our variables. So we got our 40 and our V2 and our volume.
Let the board go. Oh, let the board.
And what should our unit be at the end? Kelvin. Okay. Now, after Friday, the only equation you're going to get is PV equals nRT. That's why you need to know how to rearrange these things. Okay.
Good God.
It's easy, I know, right? It's a piece of cake.
The other ones, right?
I wouldn't memorize them because we won't always use those from afterward. Now, this is showing how we got to that equation. Or to, in this case, who is this, temperature and volume? Does anybody remember whose law that is? Charles, yeah. And you don't have to know that, but you should be able to look at these two equations and be able to go from here to here. Okay. Now, on the test or quiz, what's in the box is the minimum that I need to see. So the variable you're looking for, the variable is rearranged. How you get there, okay, you may have to do some side work to get there. Okay. But what I don't want you to do is go, oh, wait a minute, this is exactly the same thing we did beforehand. True, but you're only going to have these equations to work with. Okay. All right. So let's look at the next one, which is a little more. So let's look at the second example. And again, we'll have our before and after set of conditions here. Okay. It says a sample radon gas at 300 kilopascals. Now, what is that?
Pressure.
Pressure. So we have to recognize from this point on what these things represent. So I'm not going to say it's a pressure of, or a volume of, or a temperature of. You're going to have to recognize, oh yeah, kPa deals with pressure. Okay, so we have our initial pressure at 120 degrees, so that's our initial temperature. So we have a pressure temperature, and we didn't have any of those yesterday. And it cools down to 80 degrees. So that's our T2. The question is, what new pressure, question mark, is required to increase, oh wait, I'm looking at the next one, is the new, sorry, what is the new pressure if the number of moles in the volume remains the same? So V1 is equal to V2, N1 is equal to N2. Okay. And again, this is to help you get organized, because we'll be using more than two variables down the road. We could actually have something for every one of these, which would be fun. Yeah?
Do you have to change the degrees Celsius to Kelvin?
You must, before we do any calculations. So you've got to convert the degrees Celsius to Kelvin. Oh, yeah. And so we've got 393 there. And what is that one? 353? Okay, so always work in degrees, or I'm sorry, in Kelvin. All right, so we're looking for P2. So are we going to, sorry, are we going to divide the P's on both sides or the T's on both sides? The T's, very good. We want P on top. So if we start off with P1, V equals nRT1, we want to move T1 down. So we're going to divide it on both sides. So we have P1 divided by T1 is equal to NR. Okay. And then again, we're trying to get all the knowns on one side and all the unknowns on the other side. What I don't want you to say or interpret is that all the knowns must be on the left side and all the unknowns must be on the right. That is not true. Okay. The variable that we're looking for needs to be on top, or else you get the inverse of your answer. So we'll divide volume on both sides. So now we have P1 over T1 is equal to NR divided by volume. You'll do the same thing for the 2's. I'm not going to, because it'll get you P2 over T2. The N, the V don't change. The R is a constant, so we can ignore those. So our equation now looks like this. P1 over T1 equal to P2 over T2. And which variable are we looking for? Okay, so we're going to multiply T2 on both sides. So we have P2 is equal to P1 T2 over T1. Pretty simple, right? Yeah.
I think I want to kill myself.
Oh, don't do that. That's pretty harsh. And then once you have the variables rearranged, plug them in. So you have your 300 kilopascals. I'm sorry, yeah, kilopascals. Your T2, 353. And then your initial temperature, 393. And P2 is equal. So around 269. Okay. And again, what's in the box is the minimum you need to show to get full credit, but you may need to do more to get to that point. Okay? Especially if you're, and don't cross multiply numbers. That's not what we're doing here. Don't ever do that. Always get your variables set up before you plug any numbers in. Okay, yeah.
Okay, So like, when you're in your beginning steps, and it's like, you know that B1 and B2, you don't know, so they're equal.
Correct.
And you're gonna cancel them in the future anyways. You
Correct.
Write it down in the formula.
Nope. Again, what's in the box is the minimum that I'm gonna look at or care about. So if you do all this, it might give me some idea if you had this wrong, what you did wrong, and I could probably give you some partial credit for that. Yeah, the only thing that's going to be graded is right here. So how you get to that point, okay, is up to you. Okay. Some need to show all those steps, some just can look at a problem and go, oh yeah, I'm gonna do, got it, boom, and go. Okay. All right, so the homework are the 1s and the 2s. This is for the video thing. So your final pressure is 269 kPa. Perfect.